Today I will present my linear algebra project about panorama stitching, and the goal is to construct a single panoramic images from two overlapping images of the same scene, and mathematically each image can be represented as a matrix. So the input data is two images, and the goal is to produce a larger panoramic image, and every pixel's location in the image can be represented as a 2D vectors with coordinate x and y, and however perspective transformation cannot be expressed conveniently using only 2D coordinates. This is why we use homogeneous coordinate, where each point is represented as a 3D vectors. And this allows us to describe geometric transformation using matrix multiplication, and instead of comparing all pixels, we detect distinctive future point called key point, and key point correspond to corners or textured region that can be reliably detected in both images. And in my project we will use ORB algorithm, which stands for oriented fast and rotated brief. And first it detect a key point using fast detector, and for candidate pixel pixel x and y, we look at intensity value of the center pixel and compare it with intensities of 16 neighboring pixels arranged in a circle. And if several neighboring pixels are significantly brighter than the center pixel or significantly darker than the center pixel, then the point is classified as a key point. And the reason is that corners usually produce strong local intensity changes, which make them stable feature for matching between images. And after detecting key point, ORB estimate their orientation. And this step is necessary because the camera may rotate, and we want the descriptor to remain consistent. And to estimate orientation ORB, we compute intensity moments within a small punch around the key point. And from this moment we can compute intensity centroid. And the orientation angle is then calculated as theta equals. And these angles indicate the dominant direction of intensity variation of the local image patch. And once we detect key point, we need a way to describe them, and ORB use a brief descriptor. And instead of storing the full image patch, brief compares the intensities of multiple pairs of point inside the patch. And we can rewrite it. For each pair we store either 0 or 1, depending on which pixels is brighter, and after many comparison we obtain a binary vector. And this vector serves as a compact descriptor of the local image structure around the key point, but the standard brief descriptor is not invariant to image rotation. And to solve this issue, ORB rotate the sampling patterns according to the previously computed angles theta. And the rotation is performed using the rotation matrix. It can be written. And this means that the point pairs used for compression are rotated directly, and we can rewrite them. And we can subtract new values into our descriptor, and we will, as a result, the descriptor becomes rotation invariant. And after computing descriptors for both images, we need to find correspondence between them. And since the descriptor are binary vectors are similar, differ between two binary vectors. If the difference is small, the descriptors are similar, and the corresponding key points are likely to represent the same physical point in the scene. And this process produced a set of matched point pairs. but even if we correctly match point, the geometry of two images may differ because camera motion and perspective, and to align the image we estimate a homography matrix. And I will write it here. And to solve this matrix H, we must convert this into a system of linear equation. And if we multiply the matrix out, we will get a new equation. And now we organize this into giant matrix, and we separate the things we know, like the pixels coordinates x and y, from the things we don't know, like the h value of our homography matrix. And every single matching pair of point gives us two rows in this matrix. And so our whole system is just h equal to 0, but it's just a branch of zeros that it is useless. So we add the rule: the magnitude of h must be exactly 1, and to solve this SVD breaks our big matrix A into 3 pieces, like. And here U and V are orthogonal matrix, and sigma is a m by n matrix with singular values of A on its main diagonal and zeros otherwise, and we can rewrite it like. And the solution for H is simply hiding inside that V matrix, specifically the right singular vector corresponding to the smallest singular value. And our ORB algorithm can give us a few bad matches. Even one bad point will completely ruin our homography matrix. And to fix this, we use algorithm called Transac. And to remove outliers, it's essentially a voting system. It randomly picks 4 points, build a homography model, and count how many other points fit this model perfectly, and repeat this n times. Choose the model with most votes, and like in layer. And once Transac give us the perfect homography matrix, then we apply it inverse to the first image, and we mathematically warp every pixels from image 1 into the coordinate system of image 2. And this is how linear algebra stitches together a panoramic photo, and we can write the formula for this. And that is all.